This begins a session of TK Academy, which is Team Knowledge for Architects and Designers. This is a core competency course, which is a back to basics refresher, and the topic is Soils and Geotechnical. Here are the learning objectives for this course. After completing this course, you will be able to explain soil gradation and the difference between well and poorly graded soils. Identify the soil properties determined by the Atterberg limits. Explain the California bearing ratio and what each end of the scale represents. Recognize the Unified Soils Classification System, the USCS, and identify the letter abbreviations for different soil types. And recognize the parts of a soils report generated by a geotechnical engineer. Humans are land-dwelling creatures. We almost always have the earth beneath our feet. But most of us give very little thought on what that soil material is. Soils are made up of four major components, which can be categorized as soil solids and porous space. Soil solids are made up of minerals and organic matter, while porous space includes air and water. The degree in which each of these components make up the composite will vary upon the soil type. The greater amount of soil solids, the greater the density of the soil, which results in the greater the strength of the soil material. Soil solids are categorized based upon the particle grain size and shape. The soil's particle grain size will determine whether it is a coarse grain or fine grain material. Coarse grains include gravel and sand, while fine grains are silts and clays, with gravel being the largest particle size, down to clays being the smallest. Coarse grain materials can be compacted into a greater density than fine grain soils. Soil solids can also be classified by the particle shape as either platy or bulky. Platy particles are typically flat saucer shapes that are considered unstable because they tend to slide and shift over the surface of each other. Bulky particles are more irregular and can vary from very angular to very rounded shapes. Bulky materials, especially those that are more angular, tend to be more stable as the shapes lock into each other and keep them from shifting and moving. The method that is used to determine the particle sizes represented within a soil sample is through a sieve analysis. A sieve is a metal pan with a wire mesh grid installed on the bottom of it. Larger sieves are designated by the size of the actual opening within the wire mesh and can vary from 3 inches down to 1/4 inch. Smaller sieves are designated by the number of openings per linear inch and will vary from number 4 being the largest down to number 200 being the smallest. These sieves are stacked on top of each other, with the larger sieves being at the top and the smallest ones at the bottom. A soil sample is placed on the top sieve, and then the entire sieve stack is shaken and vibrated. The decreasing size of the screen openings permits smaller particles to pass through and the larger particles to be retained on the sieve above it. The amount of soil material that is retained on each sieve level represents the particle sizes that are present within that soil sample. When the sieve analysis is complete, each sieve is taken and the amount of soil sample that is retained on each sieve is measured as a percentage of the total weight of the entire sample. The results of the sieve analysis are recorded on either a tabular form or plotted graphically. On the table on the bottom left, you can see that there were 5 different soil stations set up for the sieve analysis. The amount of material retained on each one is recorded as a percentage and is measured in grams. And over on the far left, you see the sieve sizes that are recorded here, 8, 16, 30, and 200 being the smallest. And the amount, again, this is percentage, that is retained on each sieve. So on sieves 8 and 16, we had 4.12 and 4.31 respectively, and that equals the total amount of coarse material in that soil sample is 8.43. On the number 30 sieve, we had 6.83 and 53.32% retained, and that equals to the medium coarse materials equaling 60.85%. Pan is the amount of everything that had went through the smallest sieve, which was 200, and that percentage was 30.72. That results in the amount of fine coarse material or fine grade material at 30.72% of the total sample. Another example, let's look at station number 3, sieve analysis. Again, percentage of material, the amount of retains measured in grams. So on the number 8 and 16, we had 4.89 and 6.82 percentage that was retained on those two sieves. That equals the coarse material in that soil sample as 11.71. The number 30 sieve, we had 7.07 percentage retained on that. The number 200 sieve was 50.01% retained. So that equals the percentage of medium grade materials on that soil sample as 57.71. The pan, or the amount that fell through all those sieves, was 30.58%, and that equals the amount of fine grade materials in that soil sample as 30.58%. So we have coarse material is 11.71%, medium 57.71%, and fines 30.58%. Another way to look at this is from a plotted graph, as you can see here from the bottom right. And on here we have the particle size being indicated at the bottom from the smallest 0.001 all the way up to 100, and this is measured in millimeters. And then on the vertical side we have percentage of particles smaller than the size shown. So the way we can read this is particles that are 10 millimeters, we had 100% pass through that sieve. So we know that 100% of those are 10 millimeters or smaller. Coming down here, 0.01 millimeters, read this chart, we have about 58% of the material passed through the 0.1 millimeter particle size. And all the way down here to 0.01 millimeters, we had about 30. So about 30% passed through that sieve. So we know that they are that size or smaller. Soil gradation is the term used to describe the distribution of different particle size groups within a soil sample. You will either have well-graded soils or poorly graded soil. Well-graded soils have a good representation of a full range of particle sizes from the largest to the smallest. Poorly graded soils are those that contain a very narrow range or has soil particle sizes that are all approximately the same size. The reason that we use the term well-graded because it is typically preferred in a construction project to have soils that are diverse in their particle size because they can be more compacted into a dense mass with minimum voids and become a much more stable base. You will see on this image that the example on the far left of poorly graded has large particle size, all approximately the same size and shape. When you combine these together, you can see a number of voids that exist between the soil particles. That is where voids can have a tendency the particles to shift and to move or to contain a large amount of air and water, which are not structurally sound. The example in the middle is also poorly graded. It's a smaller particle size, but they are still all approximately the same size and shape. You can see here that when they are combined, it looks like a pile of ball bearings, so the soils have a tendency to move and shift around quite a bit. The example on the right is a well-graded soil where we have a diverse range of soils, sizes, and shapes. When these are combined, the smaller particles tend to fill in the smaller voids so that the soil particles tend to lock in with each other and can become more compact and more dense. Well-graded soils have three distinct advantages over poorly graded soils. The first, in well-graded soils, the solid mass is denser because of the interlocking of particles, which enable it to support greater loads. Remember earlier when we talked about particle shapes, The more angular the shape, the more stable it is because of the ability to lock together. The second advantage of well-graded soils is that since the particles are fitted, it realizes the best downward load distribution. Unlike the example in the middle of the picture where we have a bunch of fairly round, poorly graded soils which shift and move a lot when a load is applied to the top of them. Well-graded soils are locked together and they are going to more evenly distribute that load downward without any shifting. The third distinct advantage of well-graded soils is the tendency for displacement of individual grains by either loads or moisture is minimized because they are locked in place. Unlike the example that we see on the left of a poorly graded soils where there are a lot of voids because of the large particle sizes, water and air can get trapped in those voids. This situation causes the tendency for soils to shift and move around in those voids. A well-graded soil minimizes the voids because the smaller particles fill in the space between the large particles. Whenever dealing with a construction project, there is always the tendency to want to have well-graded soils because of the stability of the platform that it provides. Another characteristic of a soil is the angle of repose. The angle of repose is the steepest angle relative to the horizontal plane to which a granular material, such as soil, can be piled without slumping. So for example, if you can pile soil in a single place, the angle of repose is the angle that it can maintain before the pile starts to slump down and become more flat. The previous discussion about soil gradation has a big impact on the angle of repose. Well-graded soils will have a steeper angle of repose, while poorly graded soils will tend to slip and slide and have a low angle of repose. Moisture content will also have an effect on the soil material's angle of repose. Water is one of the components of soil. All soil has some water. The amount of water content determines what the physical state of soil is. So it can be solid, semi-solid, plastic, or liquid. The measurement of water content of soil to establish its distinct behavior and engineering properties is called the Atterberg limits. The Atterberg limits define a soil's shrinkage limit, plastic limit, and liquid limit. According to the Atterberg limits, a soil is in a semi-solid state when the limit of soil moisture is to where the material will crumble underneath pressure. The soil's plastic limits, which is represented by the letters PL, is the limit of soil moisture where when a pressure is applied, the material will deform and remain in that shape, very similar to a clay. The soil's liquid limits, which is represented by the letters LL, is the limit of soil moisture to where the material begins to flow underneath its own weight or perform like a liquid. The Atterberg limits are used to define the soil plasticity. The plasticity index, which is identified by the letters PI, is simply the liquid limit LL minus the plastic limit PL. The plasticity index is used to measure the plasticity of soil. Non-plastic soils have a very low index of 0 to 3. Slightly plastic soils have a higher plasticity index reading between 3 and 15. Medium plastic soils range between 15 and 30, and highly plastic soils are those that have a plasticity index above 30. Soils with a lower plasticity index have low compressibility, while soils that have a higher plasticity index have higher compressibility. Moisture content not only affects a soil's physical state and its plasticity behavior, but it will also cause a tendency of a soil to swell and expand. Soil swell is the characteristic of a soil material to undergo volumetric expansion after it has already been compacted and then subject to subsequent moisture saturation. Soil swell is measured by the free swell index, which is expressed as a percentage of change or swell as measured from the sample's initial height. Objectionable swell is that when in excess of 3%. The plasticity index, or PI, is an excellent indicator of the potential of expansive soils. A soil sample with the PI between 0 and 14 is considered non-expansive. A PI between 14 and 25 is considered marginal. A PI between 25 and 40 is a potential for critical swell, and a PI over 40 is considered highly critical for soil swell. A good rule of thumb is, when encountering an expansive soil on a project site, the first consideration should always be to build somewhere else. As architects, we are the utmost concerned with the soil's strength. That is because the building structure system is designed to transfer the loads through the superstructure into the foundations and ultimately into the ground. The soils must have the ability to withstand that load that's being transferred into it. Soil strength is defined as the shear resistance quality of the soil material and is related to the soil's ability to withstand load. The closer the soil material is to the load, the greater the soil strength must be to withstand that load. In the diagram to the right, you can see the yellow highlighted area directly underneath the footing, where the majority of the load is being transferred through the footing into the soil. This creates a soil pressure which diminishes with the depth of the soil beneath the footing. At a depth that is approximately equal to the width of the footing, the soil pressure is diminished by 1/2. Doubling that depth, the soil pressure is cut by 2/3. The soil pressures are diminished because of the loads being dispersed throughout the soil. This dispersion of loads happens at an angle approximately 45 degrees from the edge of the footing going outward. All the soils that are located in this trapezoidal area directly underneath the footing are key in resisting the loads that are being transferred from the building into the ground. This is why when excavations next to an existing building, it is important not to disturb any of the soils that is within this area, as measured from a 45-degree angle from the edge of the footing. The soil strength, or shear resistance, is measured by the California bearing ratio value. The California bearing ratio is a scale that goes from 1 to 100, 1 being the lowest strength and 100 being the highest strength. The method in which a California bearing ratio is determined is by forcing a steel piston with a 3 square inch head into a soil sample at a rate of 0.05 inches per minute and measuring the required force to penetrate that soil sample. Up to this point, we have covered the different components that are present in soil. We have gone over different particle sizes and shapes and how they work together in a well-graded or poor-graded system. We have gone over water content in soil and how it varies in the soil's performance. And we have reviewed the importance of soil strength. Soil classification is a way that we can make sense out of all this information and provides a somewhat level of predictability on how a certain soil type is going to perform. The most common soil classification system used in North America is the Unified Soil Classification System, or the USCS. The USCS takes a broad stroke at defining soil types into 3 major classification groups, the first being coarse-grained soils, which includes sands and gravels, fine-grained soils, which are silts and clays, and finally organic soils, or peat. The USCS establishes a 2-letter abbreviation system to describe each soil type. In the USCS classification system, the first letter designation is used to define what the overwhelming soil property is based upon particle size. Within the coarse-grained soils, we have G and S, which stand for gravel and sand respectively. The fine-grained soils include M and C, M which stands for silt and C for clay. And finally we have O, which stands for organics. The second letter designation further defines what the soil properties are. This could be one of the previous designations of gravel, sand, silt, clay, or it can further define the soil properties with P and W for poorly and well graded, and H and L for high plasticity and low plasticity. The chart on the right here shows the typical USCS classification table. The upper part of this table are your coarse-grained soils, and it is defined by this line that separates the chart from the fine-grained soils at the bottom, and then another line which then identifies your organics. The second level of classification then gets into your gravels, which is separated by this line, and then your sands. Both fall within the coarse-grained soils. On the fine-grained soils, same thing, we have silts and we have clays. It continues to further define this by your two-letter designation, defining what the additional properties are. For this example, up here is GW, which is gravel well graded, and then GP, which is gravel poorly graded. These classifications can use two different designations for different particle size. For example, here we have SM, which stands for silty sand, and SC, which stands for clayey sand. From these different classifications, there is usually a description that says how to expect that particular soil to perform in particular situations. Coarse-grained soils, such as gravel and sand, are very strong, stable, and drain well. They are great for foundations if they are well graded. Silt and clay are susceptible to swelling, heaving, and slipping. Building foundations must be protected from freezing and moisture. Organics are not acceptable for buildings or foundations and must be excavated and removed from the building area. A second method of soil classification is the soil texture triangle, and this comes from the U.S. Department of Agriculture, the USDA. Unlike the USCS classification, which is primarily for engineering properties, the USDA soil texture triangle is used primarily to determine plant suitability. In this method, soils are organized into 12 different soil classes. These soil classes are based upon physical texture and particle size. Each soil class has particular properties that may or may not be desirable for planting materials. There are some similarities between the soil texture triangle and the USCS classification system. For example, the different particle classifications of clay, silt, and sand. This triangle is read by knowing the percentage of clay material, percentage of silt material, and the percentage of sand material that is in your soil sample. From here, then, the clay is read as a horizontal line going across a triangle, the silt being a diagonal coming back toward the corner, and the sand being a diagonal read the other way. So for example, if we start here and we know that we have a 60% clay material and we have 30% silt, where these two lines intersect, and then we also follow this down to 10% sand. So this soil will be a 60, 30, 10 mix, which falls within the clay soil class. Another example would be if we had a soil sample that we knew was 40% silt, we follow this diagonal line, and we knew that it had about 40% sand, so it intersects where we have 40% sand, and then that means it's 20% clay. That, where these three lines intersect, places it in within the loam soil category. Again, each one of these soil classes has particular traits, characteristics, and performance. This can be matched up with plant material that may desire those certain characteristics within a soil in order to thrive well. But we know that soils are not homogeneous. We learned from a very early age in elementary school that soil has stratification, or layers. These layers are called soil horizons, and they are various in naturally formed soils. Not all soils are the same. They vary greatly depending upon location. So the arrangements of horizons or layers within the soil is known as the soil's profile. A common trait among all soil profiles is the thin horizon of organic material at the top. We call this topsoil. Topsoil is commonly rich in organic material as it contains the decomposed material of prior plant life. The topsoil layer is very thin, usually only about 0 to 2 inches thick. Topsoil is not suitable for engineered material, but it is desirable for maintaining plant life. Therefore, on most construction projects, the topsoil is stripped off and stockpiled to the side while construction work occurs, and then the topsoil is brought in and placed back on the top as a thin layer in order to maintain plant life. Beneath the topsoil can be several layers that form the soil profile, but generally these are categorized into 3 major horizons. The first being the surface or the topsoil, below that is the subsoil, and the final layer underneath that is the substratum. On any design and construction project, it is critical to know what the soil characteristics and properties are before commencing work. A soil survey must be conducted as one of the first steps. A soil survey is the gathering of soil samples for examination, testing, and classifying soils. A soil survey includes gathering data on location and classification of soil layers or profiles, the conditions of the soils that are in place, drainage characteristics, depth of the water table, and depth to bedrock. The soil survey is typically conducted by a geotechnical engineer, and it is conducted in 3 phases. The first phase is the site evaluation. This is the on-site visual assessment of the soil surface. In this phase, the geotechnical engineer is looking for visual clues of what may be going on with the soil. Things such as vegetation, surface water, and more importantly, soil contamination. The second phase is the research and investigation of existing information. This can be obtained in resources such as geological maps, agricultural soil maps, and aerial photographs. The first 2 phases pertain to soil information that can be obtained at the surface. But what is probably more important is the information that cannot be seen, that which is underneath the ground surface. To obtain this information, the geotechnical engineer must undergo the subsurface investigation phase. This information is obtained by drilling boring holes into the ground, taking soil samples, and performing laboratory testing on the soil samples. Drilling boring holes and taking soil samples can be equipment heavy and labor intensive. Therefore, there should be a number of considerations to weigh before mobilizing a boring team on a project site. The first one being the number of boreholes and soil samples that are required for the project. The cost of creating a borehole and conducting testing should be weighed against the potential risk of not understanding what is occurring in the subsurface. Diverse sites with a lot of variation pose greater risk and therefore warrant a greater number of boreholes and soil samples to be conducted. Likewise, projects with large footprints can have a lot of subsoil variation, therefore a greater number of boreholes and soil samples should be conducted. This leads us into our next consideration, the location of the boreholes on the site. The geotechnical engineer needs to have some basic design information, such as the probable location of the building on the site, the approximate footprint of the building, the number of stories, and whether or not there is a basement included. This information will help determine the location of the boreholes and the number of boreholes that should be required for the project. The final consideration should be the timing of the year for which the sample was extracted. Subsurface soil information can vary depending upon the timing of the year. It should take into account things such as seasonal ground moisture, which is typically higher in the springtime. A boring log is generated for every borehole and soil sample that is conducted on the site. The boring log includes a graphical depiction of the soil investigation findings. The information included on a boring log typically includes the depth of the borehole, the elevation and thickness of the soil layers that are encountered, elevation of the groundwater table, elevation to the bedrock, and description of the soil types that are encountered. From the information obtained from the soil sampling and testing, the geotechnical engineer will gather their findings and recommendations into a soils report. The soils report then becomes the basis of design for certain systems such as foundations and pavement designs. Most soil reports are consistent in their contents and formats. The first part is the introduction. It includes the general description of the project, the extent of the proposed construction, and purpose and scope of the investigation. The second part of the soils report includes the site description. This will include description of the location of existing facilities. It will include the topography, cultivation, and drainage on the site. The third part is a review of the area geology, and it will include regional geological characteristics and site area specific geology. The fourth part of a soils report will include the findings of the subsurface investigations. This will include the field explorations and tests, which are typically documented in the boring logs. This part of the report will also include the findings from the laboratory analysis. This section concludes with the results of the field and laboratory investigations of the soil samples. The fifth part of the soils report is the conclusions and recommendations. This part of the report is the most pertinent to the design team. In this part of the report, the geotechnical engineer will provide the recommendations for certain systems such as foundation design, floor slab design, pavements, earthwork recommendations, and dewatering and surface drainage. Designers such as structural and civil engineers rely on this information to form the basis of their designs. It should be evident that the geotechnical engineer forms a critical part of the project team. Although the design team relies on information provided by the geotechnical engineer, they are typically hired by the client or owner separate from the design team or general contractor. This is partially because the owner is responsible for providing the design team with all the information regarding the project site. Because the soils report provides vital information going into the development of design, the geotechnical engineer is often one of the first individuals that is involved on a design and construction project. Although a soils report is generated early on in a project schedule, the geotechnical engineer is typically involved during construction for material testing, compaction testing, and earthwork quality control. One final thing to keep in mind is that the geotechnical soil reports are project specific and they should not be used interchangeably even if the project is on the same site. This concludes this TK Academy course over soils and geotechnical. Hopefully you enjoyed this course. If you did, please give it a thumbs up and leave us a comment. You may also want to subscribe to our YouTube channel for more courses like this and other content from TK Architecture.